Thank you again for the kind introduction. And today I'll be talking about batteries and how I look inside them to see how they work. Now, a bit about me. I have been all over the country, going from one place to another, to another, to another, and I'm going to be going to Detroit this summer, but I travel a lot. I see a whole lot of different kinds of things, and as an amateur photographer, I take a lot of pictures. Going from the mountains in the Grand Tetons to Denali in Alaska, Red Rocks in Colorado, the North Carolina coast, and recently, the cherry blossoms in University of Washington. And looking at things artistically like this is very related to what I do in batteries, except it's a lot harder to look and take pictures inside of an electrochemical cell as it runs. Taking apart batteries is generally frowned upon. However, without being able to know what goes on inside them, we cannot make them better. And as we approach the great clean energy transition and more use of solar power, it's very important that we do. So to recap a little bit about what we use batteries for, I'm pretty sure you're all familiar with the way we use batteries in everyday life. As a way of storing electrical charge, they're invaluable for everything from computers to all the lights we're using to phones and even the AirPods with tiny little batteries that we can fit to power these tiny devices, like these extremely convenient headphones that I was wearing. More and more these days, we're also talking about transportation. Electric cars are not as much on the rise as they were a few years ago, but there's still innovation and development constantly happening, driven by these auto manufacturers. I mean, I'm going to work for General Motors this summer. So it's a very, very rich field. And if you can get batteries good enough, electric planes start to become more and more feasible. Finally, renewable energy is fantastic. Solar energy and wind energy are fantastic ways to renewably get energy from the world around us. But we cannot control how much solar or wind we get like we can with a generator. We need ways to take power generated at peak times, like noon, and shift it to the cold, rainy days or December where that power is really needed. Last December, a bit north of here, Puget Utility had to buy energy, spend hundreds of thousands of dollars buying energy from surrounding utility services because despite their renewable energy generation being almost at 98%, they didn't have enough energy for the coldest months of December in these last few years. Okay, that all aside, let's talk about what's the issue is with batteries right now and why we want to make them better at all. So first of all, batteries degrade over time. You might have noticed that after you buy a brand new phone, it lasts for like 2 or 3 days, and it's pretty great. And you don't have to worry about charging so much. But as you go on and on and on, this becomes less the case. I mean, I've had this thing for about 5 years now, and, well, I bring a backup charger with me wherever I go. The reason is because every time you charge or discharge a battery, you're not picking up quite as much energy as you did before. Now, they've gotten these to be really good. They're like 99.999%. But even those, when you're talking about a device, that adds up. And the way you charge it also makes a difference. Now, ideally, we like this blue curve, which we charge it slowly and discharge it slowly, and it lasts for a long time, and it's fine. However, we like to have our batteries not take 10 hours to charge. So we introduced fast charging, and as you go charge the battery quicker, you see quicker degradation. A lot of the engineering that goes into phone batteries has to go into engineering how to make fast charging work better. It's a very difficult challenge, but it would also be easier to just make the batteries more able to cycle for these longer periods of time. So that's the first thing we want to do. We want to make batteries that are able to charge and discharge quickly, but keep that energy and not burn out over maybe like a dozen cycles. The other thing we're interested in is replacing the materials inside the battery to be more useful. Anything that is not lithium or any active material in the battery is not giving you energy. That includes everything from the separator, I could name 100 little different components that all add up to, make this energy. But we don't want to waste valuable weight on things that are not helping us store energy. This gives you just a bit of a rough idea of like the composition of a battery. On the very, very top, you can see about 7% is lithium. The reason why cobalt is highlighted on this chart is another reason we want to look into alternative ways of doing this, because there's a lot of ethical and cost issues with all the cobalt that goes into batteries used by, say, Tesla. So to summarize all of that I've just rambled at you about, we want to raise the amount of energy we can store in the same space, and we want to make it last longer. In order to do that, we cannot just randomly try things, because that's what I did when I was a kid, and I set a lot of things on fire. And my boss would be rather angry if we had another bomb squad that we had to call in. So we want to understand how the battery works before we do anything crazy. We want to then engineer what's inside of it, and then we need to figure out if it worked. So let's start with the first box here, understanding how a battery works. We've all got this general idea of a positive and a negative end. This is a good way to view it because generally you have a high end and a low end. And lithium's job is to jump off of the cliff. And the energy that it gets from jumping off the cliff is the energy it uses to shove an electron around the circuit. And then you push it back up the cliff, and then you charge the battery. Yeah, it's a really, really fun metaphor. And you get a lot of energy in here because, again, a fully charged battery is essentially holding on to, I don't even know how many, crazy amounts of lithium atoms, and you're just holding it over the edge of the cliff by a rather tenuous thread, depending on how stable your battery is. So if there's an issue inside your battery, you can have pretty bad things happen. A lot of thermal runaway happen, and we see that in cars, or the Samsung Note 7, if you remember that, where uncontrolled runaway reactions, this energy, this holding lithium over the edge of the cliff, if it can escape in any other way, it will. So we need to add something a bit more to this rather simplistic picture of positive and negative. We need something to mediate the charge that goes in between. And yes, I did ask if it was possible to make a battery with Gatorade as the electrolyte. It's not. Because the job here is to mediate the flow of ions. An electrolyte's job is to let lithium flow back and forth, but not electrons, because then that's a short circuit. We want electrons to go around the circuit, not inside the battery. This electrolyte isn't part of the high and low end that defines the energy you get, but it is what's really holding the cell together. And it's the medium by which the ions are falling. Let's take a step a bit away from the electrolyte again, and I want to talk about the positive and negative side, and talk a bit about what we're actually looking at when you talk about a positive side and a negative side. Essentially, we're looking at pieces of shelving. Their job, the anode and the cathode, is to hold on to lithium until it's ready to be dropped off the cliff or kicked back up the cliff, or whatever you prefer. Now, we have two different kinds of shelving units here. We have the one on the left, which is pretty lightweight, and we have the one on the, I have my direct, no, I was right. So we have this one, and we have this one. Now, which of these, so the one on this side, or the one on this side, which one would you generally prefer to keep your bowling ball collection on? Now, generally, I think we would all prefer this one, because I don't think I could trust a drop-shipped product like this to hold a bowling ball without the wood breaking or something to that effect. This is kind of what we see in batteries. Our battery structures, or our battery materials that we use to hold on to lithium, are really rugged. They're decently heavyweight, and they're heavyweight because we want them to be stable. We want them to not break down and cause those runaway side reactions. However, that's, again, a lot of weight that's not actively giving you more energy. We want something slimmer, but we want something that can still maintain stability. And we also want something that maybe is a bit of a higher cliff. But there's all sorts of different kinds of things. And to be able to build these next generation batteries, we need to stabilize these next generation kinds of shelving. We need to be able to fit our bowling balls on this and have it remain stable, or just stack our bowling balls without any shelving at all and have that remain stable. That's a fun challenge. There are a lot of different kinds of electrode materials. This graph is confusing. So here's what matters. You might be familiar with lead acid batteries. On our chart here, as you go up, you can contain more energy. If you go to the right, or whatever way that is, you can put out more power, so more energy per time. So right now, you might be pretty used to lead acid. It's what we use for cars because they are reliable, they are dependable, but they're not as energy dense or as power dense as lithium ion batteries. Now, right now, we are here with lithium ion batteries. Lithium ion batteries are great. We have spent decades perfecting the lithium ion design. That's graphite against whatever cathode you have with a certain kind of electrolyte. We've gotten really, really good at that. However, we're getting so good at that to go past, we need to kick out graphite and throw in something new. So, for instance, what I'm going to be working on this summer is trying to replace it with sulfur and lithium metal, which are, again, two great materials if you want to store a lot of energy, but they're not going to last very long because they're not very stable. Oh yeah, I put that there too. We're also technically up there. That's where internal combustion engines are for cars, to give you an idea of the length we still have to go. But that's not important. What is important is that as we push up towards that corner, we get more energy, but at the cost of stability. And it's these that we're interested in. Yep. Energy density higher, we lose that in terms of stability as the electrolyte breaks down more or other things happen or other side reactions happen. So all of that coming down, when we try new things, when we try out new electrodes, we try out sulfur, or we try putting in something new as the electrolyte to see if it stabilizes, besides just watching the chart, like the energy it can hold go down over time, that's useful, but it doesn't tell us what's happening inside. So to look inside, what we need to see are the interfaces that separate the electrodes from the electrolyte. In these areas, we will have things build up from side reactions that we cannot stop. But the magical thing about the lithium-ion battery, and the reason why it was so innovative, is that these side reactions managed to stop themselves. These interfaces here managed to get so full of little side reaction products that the electrolyte and the electrode couldn't touch anymore. But these interphases let lithium flow through. So it acted as a passivation layer that stopped thermal runaway, stabilized the cell, and let this function, even though it was itself just made of a bunch of side reaction products. We call these interphases. There's one for the cathode and one for the anode. And the structure of this interface will more or less tell you if your battery is going to be stable or if it's going to just continue to decay until it dies from these side reactions. So the question might be, okay, let's go in and see what it's made of, and then we'll just deposit that on all of our electrodes, and then we can just throw it together and we don't have to rely on this chemistry. This is what it looks like, to give you an idea. You have all sorts of side reaction products from these really, really hard oxides, fluorides, carbonates, more fluorides, to this soft stuff, this polymers and more semicarbonates, all sorts of a mess that ends up depositing on this tiny layer. And it's not a thick layer. This is maybe only a dozen or maybe 100 atoms thick total. This layer is chaos, but this is what we need to engineer in order to stabilize it. If we can understand, predict, and control how these interphases react, we can make these batteries stable and actually go forward with presenting it. But as I said before, these are tiny. Someone brought up human hairs earlier. Well, I have scaled, typically, how thick a battery is to a human hair. Again, it's about 100-something microns thick. Batteries are manufactured extraordinarily thin nowadays. This is a roughly to scale. Again, same figure, squished down to actual size compared to a human hair. And you can just barely see the interfaces here. There's faint lines of blue and red. So what I'm going to be talking about is my approach to looking at these interfaces, because it is not easy. Now, when we talk about looking things under a microscope, we have a lot of options. Light is not going to cut it. The things we need to look at are too small for light to detect. Now, electron microscopes have a better shot. In fact, there's a lot of cool work that's being done using electron microscopes to, oh, I bet I don't, this will not play. Electron microscopes can see it, but this requires shooting your very, very delicate, sensitive interface with 400 kilovolts of electron beam current. And you can do all of this work to prepare your special cell and set it up for the beam, and you can get some really cool stuff. On the video that is not going to play because I forgot to upload it correctly, it was actually a video of lithium entering into a silicon chip. And you would see that ball swell and contract as lithium went in and out. The things that people can do with electron microscopes are really cool, but it's a very difficult and very expensive tool to use. You can get some cool stuff off of it, though. Here's one of these interfaces that I'm talking about. Here you have some electrolyte, or electrode structure, and if you take a look at the difference between this red area, this area over here, you can see there's a bit of a texture change right here. This is the interface. This is that tiny little layer that we're interested in. And when the electron microscopists do their black magic, they can analyze some cool chemical stuff about that. But this is not the method that I'm using. I want a method that is more delicate. I want a method that we can actually use looking at an electrode that actually has electrolyte on it, and we can actually charge and discharge like a normal battery. I'm using a method that uses touch as opposed to light. The method of atomic force microscopy, that's a mouthful, is something I call the world's most sensitive record player. Now, if you take your hand and touch literally anything, you'll get more information other than the fact that there's an object here. I don't have to look to feel that this is cold, this is hard, and my instincts tell me it's probably made out of metal. You can't get that information by looking at something. I'm looking at it now, and maybe that could be made of plastic. By feeling instead of looking, the tip of an AFM can feel these little variations in hardness, these little variations in how much it'll hold onto the tip, how rubbery it is. And it's a lot of information that's completely different than what you get from an electron microscope. And what I aim to do with this is put this microscope in a nice sterile environment that my batteries won't explode if I open them in it. And then I want to cycle a battery while this record player is going over the surface, measuring all of these little mechanical signatures to see if I can tease out, by whether it's hard or soft or anything like that, what one of those myriad of different phases are forming as I'm cycling the battery. Here's what AFM data can actually look like. Here's a kind of a cool study one group did, where they took an electrode and they charged it and discharged it, and kept on charging it and discharging it. And look in the corner here. You can see as they kept on cycling it, you can see this cracks start to form. This is the kind of decay that can lead to capacity loss, is you have these cracks start to form from taking in lithium and letting it go, and taking it in and letting it go. This is just a topological map, just measuring, how high is the tip going. But AFM can do more than that, because as I said before, it can measure how hard something is, how soft, all of these touch sorts of things. This is AFM of a DVD. On this side, you got the height. So you have all of these little holes that are, according to the scale, about 260 nanometers tall. But if you look on this figure over here, what this is telling you is actually about the hardness and the softness of the various parts. And you can tell that the AFM tip kind of catches on those bottom and top sections because all of a sudden it looks very different. This is the information that I want to try to look at. From this kind of AFM image, I want to take this color that represents all of these little details about the mechanical properties of the interface, and I want to just touch it and be able to tell what some of these different components are. If I can do that, then I don't have to blast them with a beam of electrons. I don't have to go through way too complicated processes to figure out what's going on. And in time, I'm hoping that I'm actually able to make a chemical map as the battery cycles and as this layer grows. I want to use this method to make that map kind of as it happens. And I'm pretty excited about it. However, funding for the project just came in 2 weeks ago, so I don't have anything quite yet. Right now, I am trying to teach the AFM to tell the difference between copper foil and aluminum foil, and it's still struggling. But I am pretty excited. I have some experts in the field working with me on getting this process to work, and I am extraordinarily excited. So, to summarize, better batteries make a better world. We use it in all the ways you do think of, and some ways you might not think of. We want to make better, more effective shelving and higher and taller cliffs to be able to store more energy, but we need to stabilize it. So to stabilize it, we need to make sure we understand those interphases that stop side reactions from murdering our battery while we still want them. And to look at those interphases, I want to use the power of touch to get a more accurate understanding of how all this works. Thank you, everyone.